question, we had an application of calculus, and this is specific to a tidal algae growth that happens to fall in a very unique shape, a rectangle, which we know probably won't happen, but for a simplistic purpose to apply our calculus, it's a little bit easier to do so in such a form of a rectangle. And it says whose length and width change with respect to time. So length and width change with respect to time. So since they change with respect to time, we're probably thinking about taking the derivative with respect to t. We don't know, but that's probably a hint here that this changes with respect to time. At time t, which is in hours, the length L of t and the width W sub t, which are both in meters, are given by these two values, L of t and W sub t. Let A of t denote the area of the algae growth at our time t. So part A says express A of t in terms of length and width. Do not multiply out or simplify. So all we have to do is find our area. We know the area of our triangle will always be equal to length times width. But we know our length is given by 1/3 t cubed minus 4t to the 1/2. I'm going to translate this square root to the 1/2 plus 200 times our width, which will be 2t squared minus 2t to the 1/2 plus 100. Part A done. We know the length of any rectangle is always equal to length times width. So now, in part B, we want to compute the rate of change. So again, when we see this term rate of change, hopefully we're thinking about derivatives of the area with respect to time. So we want to compute the rate of change of the area with respect to time. Therefore, we are looking for the derivative of A. So we're looking for the derivative of A, with respect to t. So we're going to take the derivative of A with respect to t. So basically we're going to find A prime of t. Either one of those would be a sufficient way to denote this. Notice we're going to have the product of two different functions. You could go ahead and FOIL those out, but I know I wouldn't want to. I'll keep it like such. So with our A prime of t, we're going to have our first function, 1/3 t cubed minus 4t to the 1/2 plus 200 times the derivative of our second function, 2t squared minus 2t to the 1/2 plus 100. I'm going to call this just prime right now. I'm going to do this in two steps. Plus the second function, which is 2t squared minus 2t to the 1/2 plus 100 times the derivative of our first function, which is 1/3 t cubed minus 4t to the 1/2 plus 200, and we're going to call that prime. So our first function times the derivative of the second plus our second function times the derivative of our first. Let's go ahead now and take our derivatives. This is still going to be our A prime of t, or dA dt, the derivative of A with respect to time. We're going to keep our first function, 1/3 t cubed minus 4t to the 1/2 plus 200. So now we are going to take the derivative of the second guy. 2t squared will be just a value of 4t minus 1/2 times negative 2 gives you just a value of negative t to the negative 1/2. And this still gives me that plus 100. Derivative of constant is always going to be a value of 1. So that'll be our derivative of the second function. Over here, we're going to have 2t squared minus 2t to the 1/2 plus 100 times our derivative first. And notice here we're going to have t squared minus 4 times 1/2 gives you a value of negative 2 t to the negative 1/2 power. 1/2 minus 1 gives you negative 1/2, and this is also going to be a value of 0. The derivative of 200 is also a value of 0. So let's go ahead and leave it as such. I don't want to multiply it out or simplify it. I'm just going to keep it like this, make it a little bit easier on myself. I'm very content leaving this form. If you want to, you could maybe simplify and get rid of these these 1/2 exponents and convert them. But that's okay. That's okay. I will go ahead and do so just so we can see it. A prime of t is equal to 1/3 t cubed minus 4 square roots of t plus 200. Over here we will have 4t minus 1 over square root of t. Converting t to the negative 1/2, I can bring this down to the denominator as a positive exponent and convert it back to the square root, plus 2t squared minus 2 square roots of t plus 100. And over here we're going to have t squared minus 2 all over square root of t. So I took this down to the denominator with a positive exponent. So either one of those are sufficient answers. So now we want to compute the area at time t equals to 4. Notice it just says it wants the area. It doesn't want to know the area with respect to time or whether or not it's increasing or decreasing. So now think to yourself, are we going to use this formula or are we going to use our second formula? Hopefully we recognize that for part C, we're going to use the formula that we found in A. So part C, we're going to find A of 4. We want to find the area at time t equals to 4 hours. So here we're just going to plug it into this first guy. So we're going to have 1/3 4 cubed minus 4 times t to the 1/2, which we'll just say is 4 to the 1/2 power. Hopefully recognize that's the square root of 4 plus 200. Still times 2 times 4 to the 2nd power minus 2 times 4 to the 1/2 power plus 100. Okay, so 4 times 4 is 16 times 4 is 64, so we're going to have 64 thirds over here. 4 to the 1/2 is 2, minus 4 times 2 gives you minus 8 plus 200. 4 squared gives you 16 times 2, which is 32. 4 to the 1/2 is 2 times negative 2 is minus 4. And then we have plus 100 over here. Hopefully I did these calculations correct. I think we did. So now let us continue here. Negative 8 plus 200 gives me 64 thirds. 200 minus 8 is plus 192. 32 minus 4 gives you 28. Plus 100 is 128. Okay, 192 is how many thirds? Let's look at that. So we'll get 6, 27, 3, 576. So this will equal to 64 thirds plus 576 thirds. Still times 128. 64 thirds plus 576 thirds. That gives you a 0 and a 1, 14, and 640. This gives us 640 thirds times 128. I'm going to take out my calculator to do this one to multiply these fractions. So I will have 640 times 128, and that gives me a value of 8,000. What was that? 1920 all over 3, and this will be, and I believe that was meters squared. So this will be meters squared. We always have to have units with this. So my area at time 4 of that algae growth will be 81,920 thirds meters squared. So that's what we're going to see. In part D, we're going to advance this one step further. We just used the area formula, and in D, we're going to have to find the rate of change. We're going to find the rate of change of the area at time t equals to 4 hours, and we have to determine whether or not this is increasing or decreasing. We're going to have to justify this. So we're thinking rate of change. Hopefully now at this point we're recognizing this is the derivative. Therefore, since we're looking at the derivative, we are going to be examining the equation in part B that we found. So I'm just going to go ahead and copy this so we can see it. So I'm going to copy this right here so we can see it. Oh wait, no, the one that we can use. I'll use this one right here. So I'm just copying it. Okay, I thought I could copy it. Maybe I can't. Okay, I'm going to get all this. So let's pop down here to part D. I don't need that there. So now we're going to find in this part, so for part D, we're going to have to find A prime of 4. We're looking for the rate of change, so we have to determine whether or not this growth is increasing or decreasing with justification. So A prime of 4 Plugging in all our values for 4, we're going to have 1/3 4 cubed minus 4 times the square root of 4, all plus 200, times 4 times 4 minus 1 over square root of 4, plus 2 times 4 squared minus 2 times square root of 4 plus 100 times 4 squared minus 2 all over square root of 4. Plugging in, I know it seems a little tedious, but again, nothing that we can't handle. We are on the path to finding whether or not this is increasing or decreasing and what rate it is doing so. 4 cubed, 64 thirds, so we're going to have 64 thirds. Square root of 4 is 2 times -4 gives you -8 plus 200. As we had that come back again, I think that was equal to 640 thirds, so this will actually equal to 640 thirds. So notice this will be times 4 times 4, which is 16, minus 1/2. Square root of 4 is 2, so we're going to have minus 1/2. 16 is really 32 halves, minus 1/2 is 31 halves. So let us continue with a plus. 4 squared 16 times 2 is 32, minus 2 times 2 is minus 4, plus 100, times 4 squared, which is going to be 16, minus 2 all over 2, which gives you minus 1. So we're going to get 15 there. Let us simplify. 32 minus 4 gives you 28, plus 100 is 128, times the value of 16 minus 1, which is 5. Let us go ahead and use our calculator for this process. So we're going to have 640 times 31, so 19,840. All over 3 times 2, which gives you a value of 6, plus 128 times 5, which is a value of 640. Let's see, does 19,840, does that divide evenly by 6? Probably not. Nope. So we're just going to have to reduce this, so we know this can, well, let's go ahead and just add this first. So we're just going to take 640 times 6 and see what this is in terms of 6. So 3,840. So this is 3,840 sixths. 3,846 plus 19,840 plus, where are we here? Plus 19,840 gives us 23,680. 23,680 all over 6. Let's make sure I did that right. This probably not, well, it won't divide evenly by 6. So we can reduce 23,680 by a value of 2. So we get 11,840. 11,840 all over 3. Notice this is going to be a rate of change. So this is going to be the units of meters squared per, I believe that was in hours. So meters squared per hours. Meters squared per hours. So notice, and this is hours, let us analyze now the sign of this rate of change. Notice here our sign is positive. Since a prime of t is greater than 0, this indicates that the area is getting larger. This actually is almost a vector form or vector notation. Since your derivative is positive, this indicates that the area is getting larger. So now, in response to this question, we know that the rate of change of this time is the value we calculated, and we know that the area is increasing at this instant because our derivative is positive. Since a prime of t is greater than 0, this indicates that the area is getting larger. Therefore, the area is increasing. And this makes sense. We don't expect the algae population to start randomly decreasing if we didn't do anything to it. So in this circumstance, our area is getting larger. It is increasing.